Welcome back. In the previous class we studied about series clippers. So today let us look at parallel clipper. So in case of parallel clipper, what we see is that the diode is placed in parallel with the load resistor. Over here RL is the load resistor. As you can observe that the diode is getting placed across or in parallel with the load resistor RL. RS is the current limiting resistor and Vs is the input source. Now in case of parallel clipper, we take the output across the load resistor. So let us say the output is V0. Okay. Now if you observe closely in this particular circuit,
voltage V0 is measured across resistor RL, and the same voltage V0 present across the diode contacts as well. Let us say this is the anode terminal of the diode and this is the cathode terminal of the diode. Since voltage across the diode as well as the load resistor is the same, so for analysis sake, we can neglect the load resistor itself. That's because the output voltage across the load resistor is same as the voltage measured across the diode. And that's the reason in many of this standard literature, for a parallel clipper, you don't find a load resistor. So it is assumed that the load resistor is present across the diode terminals. Alright, so this is your circuit of choice. Alright, so that being said, we can get into the analysis part. So just like series clipper, the parallel clipper can be found in positive clipping category as well as in negative clipping category. So first let us look at parallel positive clipper. So first let us try to analyze the circuit with ideal diode. So first let me draw the circuit. So what do you mean by a parallel positive clipper? A parallel positive clipper clips the positive half cycle of the input waveform. So it alters the positive half cycle of the input waveform. So this is your current limiting resistor, source voltage, the diode, and across the diode you are going to measure the output voltage. The lower end of the circuit is held at ground potential. Yeah, and we have assumed diode is an ideal diode. So whenever it is forward biased, it acts like a short circuit, and whenever the diode is getting reverse biased, it is going to behave like an open circuit element. So first let us consider the positive half cycle. So let's write during positive half cycle. So what happens to the circuit operation during positive half cycle? So during positive half cycle, what we can do is we can assign the polarity for the positive half cycle. So how do we assign the polarity for positive half cycle? Upper side positive and lower side negative. Then comes RS. Then comes the diode. Okay, so as you can clearly observe that during positive half cycle, the positive terminal of the source is getting connected to anode terminal of the diode, and the negative terminal of the source is getting connected to the cathode terminal of the diode. Hence you can say the diode is forward biased. So over here let me write. So whenever the diode gets forward biased, diode behaves like short circuit element, and therefore we can redraw the circuit something like this. So this is your source resistance, the current limiting resistor RS and the diode. Now the diode is getting forward biased, hence you can replace with a short circuit equivalent. And across this short circuit, basically you are measuring the voltage. So let us consider this as figure C and this as figure B, and this being figure A. So in figure C, observe the output V0. So in figure C, if we look at the output, what are we observing? We are trying to measure the output across the short circuit. So this is your short circuit. So in a short circuit, the voltage is 0. So V0 is equal to 0 volts during positive half cycle of the. Alright. So for the positive half cycle of the input, the output stays at 0 volt level. Hence you can say that the positive half cycle is getting clipped. So that is the reason it is called as a positive clipper. Now let us see what happens during negative half cycle. So let's write during negative half cycle. Okay. So first of all, you have to assign the polarity. Okay. So for the negative half cycle, we take upper side negative terminal and the lower side we'll consider it as positive terminal. And this is the anode side of the diode and this is the cathode side of the diode. Now as you can clearly observe that during negative half cycle, the positive terminal of the source is getting connected to the cathode terminal of the diode and the negative terminal of the source is getting connected to the anode terminal of the diode. So this particular connection leads to reverse biasing operation of the diode. So over here, diode gets reverse biased, and whenever the diode gets reverse biased, diode can be replaced with an open circuit equivalent. Diode can be replaced with an open circuit equivalent. So let us do that in the circuit. So in the circuit, equivalent circuit, you are supposed to open up the diode terminals. So let's see how the circuit is going to look like. So this is your open circuit. So basically during negative half cycle, you are trying to measure the output across the open circuit. So if we apply KVL, so what do we get? So current is 0, so minus 2 plus Vs, then minus 2 plus V0, voltage across the current limiting resistor is 0, that's because current is 0, so 0 into Rs becomes 0, so this is equal to 0. This implies your output is equal to minus Vs. And what is Vs? Vs is your input voltage and V0 is your output voltage. So output is basically negative of the input voltage. That means to say the output voltage is equal to negative half cycle of the input voltage. So during negative half cycle of the input, the clipper basically allows the signal to pass through. So it is not shaping the negative half cycle of the input. So only the positive half cycle of the input is getting shaped, and that's the reason we call this particular clipper as a parallel positive clipper. Now let's try to plot input and output waveforms. Okay, so first let me plot the input waveform. This is your time axis and this is your input. Plus Vm minus Vm, the amplitude of the input. And just below the input, you can think of plotting the output as well. Okay, so mark the transition points. This is the duration of positive half cycle and this is the duration of the negative half cycle. This is your output. So what did we see from the analysis? We have seen that for the positive half cycle of the input, the output was 0 volts. Output was 0. On the other hand, for the negative half cycle of the input, the output was minus Vs. So the output will be the replica of negative half cycle of the input. Okay. So what you can say is that positive half cycle is clipped. Alright. So this is your input output characteristics. You can also plot the transfer characteristics. So how do we plot transfer characteristics? So to plot transfer characteristics, we take input along x-axis. So this is the positive half cycle and minus Vs represents the negative half cycle. So positive y-axis is plus V0 and negative y-axis is minus V0. Okay. And along x-axis you can mark the amplitudes of the input on either side of the x-axis. So for the positive half cycle, the maximum value is Vm, and for the negative half cycle, the maximum value is minus Vm. Alright. And then let us look at the circuit operation. So we have seen that for the positive half cycle of the input, the output is 0. So for the entire positive half cycle, the output occupies the x-axis, right? So a line basically overlaps the x-axis. On the other hand, for the negative half cycle, the input is equal to, the output is equal to negative half of the input. So whenever you have a AC signal, there will be a slope and the maximum value of the output is minus. Okay, so basically you will get an inclined line, and the angle is 45 degrees. So this is your the transfer characteristics. All right. So now let us look at the behavior of the circuit with a practical diode. So let's see how exactly the practical diode changes the wave shape of the circuit. So let me take it as B. Let me write the heading something like positive clipper with a practical diode. So in case of practical diode, we shall consider threshold voltage of the diode. Let it be Vk. So let Vk be the threshold voltage of the diode. Okay, and then let us redraw the circuit. Source voltage, current limiting resistor Rs, the practical diode with some threshold voltage or barrier potential, and this is where you measure the output. Okay. So the barrier potential is Vk, hence what we have to do is, in place of practical diode, you're supposed to substitute the equivalent circuit. So in the previous class we have discussed about the equivalent circuit as well. So observe carefully how we are going to insert the equivalent circuit. So this is a practical diode with a threshold voltage of Vk. So all what you have to do is retain the diode symbol in as it is formed and consider it as ideal diode. Okay. And now you insert the barrier potential. So the property of barrier potential is such that it opposes the diode conduction. So to the cathode terminal of the diode, you need to connect the positive terminal of Vk and the opposite terminal is connected to the negative terminal of the barrier potential is connected to the source. So upper side of Vk is positive, so which is connected to anode of the diode. So you can say that the barrier potential is opposing the diode conduction. So this is the logic to place the barrier potential. Okay, it always opposes the diode conduction. This is your output. Okay. So now let us look at the circuit operation. So write during positive half cycle, you assign the polarity. Now, during positive half cycle, what you have to do is, you have to identify the pressure applied by the sources. Now, if you look at the input voltage source Vs, the input voltage source Vs is trying to send or circulate the current in clockwise direction. On the other hand, the second source, which is basically Vk, so Vk is trying to send the current in the opposite direction. So over here, there exists something known as the source opposition. So Vs and Vk are opposing each other. Vs and Vk are opposing each other because both of these sources are trying to circulate the current in the opposite direction. So the circuit operation basically dictated by the dominant source. Vk is basically DC potential whose value is 0.7 volt for silicon diode and 0.3 volt for a germanium diode. So it's a DC source. You can consider it as a DC source since it is having a fixed potential. On the other hand, Vs, if you look at, Vs is a sinusoidal source whose magnitude is not constant, right? So the signal Vs rises from 0 volt, reaches positive maximum, and then again it falls to 0 volts. And in the negative half cycle, again it rises to minus Vm, and then again it comes back to 0 volts. So basically, Vs is consisting of a set of instantaneous values. So in order to explain the circuit operation in this particular case, what you have to do is you have to consider the instant at which the input voltage source is less than the fixed DC potential, and also the instant at which the instantaneous value of Vs is greater than the fixed potential. So for the positive half cycle, let us split the analysis into two parts. So we shall call it as cases So case A is during which Vs is less than Vk. So when the input voltage is less than Vk, what happens to the circuit operation? So you can visualize in this manner. Okay, so this is Vk. So in case 1, Vs is less than Vk. So what you can say is Vk is a dominating source. So what do you mean by a dominating source? So uh, in simple terms, can be considered as the source which has won the battle in circulating the current. So out of Vs and Vk for case 1, Vk is basically getting a chance to circulate the current. So the dominance should be shown by putting an arrow direction. Okay. If Vk is dominating in nature, so you can clearly observe that the positive terminal of Vk is connected to the cathode terminal of the diode, right? So Vk reverse biases the diode. Therefore, diode behaves like an open circuit. Hence, you can draw the equivalent circuit. So just open up the diode terminals, retain Vk connection as it is, and measure the output voltage. So, yeah, it is an open circuit situation. So voltage across Rs is 0, and output voltage V0 is as good as you're measuring the voltage across the source, because Rs voltage across Rs is 0. So for the first condition, wherein the input source Vs is less than Vk, output is equal to Vs. So output is nothing but positive half cycle. Now let us consider case B. So in case B, what we are trying to consider is that what if the source voltage is greater than Vk. So when the source voltage is greater than Vk, what we can say is that Vs dominates. So Vs dominates in the sense Vs is trying to circulate the current in the circuit. Whether it is able to send the current or not, that is totally governed by the diode connection. So let us redraw the circuit. So that's Vk. So Vs is the dominating source. So what you can do is you can put the arrow in the direction of Vs, just to show that Vs is dominating in nature. Alright. So if you were to look at the dominating source, so what you are seeing is the positive terminal of the source Vs is connected to the anode terminal of the diode. Hence you can say that Vs would forward bias the diode, right? That's because positive of the source is connected to anode terminal of the diode. So if Vf forward biases the diode, then what happens to the circuit operation? So let's draw the equivalent circuit. So Vs is forward biasing the diode, hence diode is to be replaced with a short circuit equivalent followed by a battery. And this is okay. Now, what is V0? So you can clearly observe that V0 is measured across this node and across this node. So between these two nodes, what is present? Between these two nodes, Vk is present. So your output voltage V0 is nothing but the Vk. So V0 is equal to Vk. Say that DC value.